Today, we'll be taking a look at two simple math concepts that every child understands, each of which has powerful applications in more advanced courses. Let's take a trip down memory lane. You were much younger, maybe 8 years old, and this weekend was special. Your parents planned a trip to Disney World for you and your sister. You woke up early, put on your favorite Mickey Mouse t-shirt, jumped up and down on your parents' bed until they told you to get out, poured yourself a bowl of Lucky Charms, and were waiting at the door ready to go by 8 a.m. Then your parents said the dreaded words. "We aren't leaving for another 5 hours." How could this be? If you don't arrive at Disney World in the next 5 minutes, your head might just explode. And who even knows how long 5 hours is? To a kid, this is torture. For the next 15 minutes, you beg and plead with your parents. "But Mom, if we don't go now, we'll miss all the good rides." She doesn't budge. So you return to your room and sulk on the bed for a while, and then start staring at the clock on your desk. It's a digital clock, and it says 9 a.m., 4 hours to go. You're leaving at 1 p.m., and there's nothing you can do about it. But wait, something complex just happened in that moment. How did you know that 4 hours after 9 a.m. was 1 p.m.? Addition that you learned in school would suggest that the answer is 13 a.m., but that doesn't exist. So how did you know time works like this? Maybe you learned from worksheets at school, but the clock rolling over from 12 to 1 illustrates a fiendishly simple yet undeniably important mathematical principle. Let's see another familiar example before we take a look at the underlying concept. Here's a simple addition problem. Add the 1's digits, carry the 2. Add the 10's digits, carry the 1, and so on. You'll notice the similarities with our clock example here. 7 plus 8 plus 7 in the 1's column isn't 22 1's, it's 2 1's, and the 10's digit is carried over to the next step. A similar phenomenon happens in multiplication. This process, where we cycle through a sequence of numbers and then reset back at the beginning, is known as modular arithmetic. Now, this idea has been around for millennia, although modern notation and understanding comes from German mathematician Carl Friedrich Gauss from the early 1800s. In modular arithmetic, numbers separated by a fixed quantity called the modulus are said to be congruent. For the 12-hour clock cycle, the modulus of 12 means that 1 and 13 are congruent, as are 2 and 14 or 3 and 15. But this principle extends indefinitely in either direction. 85 hours after 6 p.m. is 7 p.m., and 29 hours before 2 a.m. is 9 p.m. To be more explicit, two integers a and b are said to be congruent modulo n if n divides their difference. So minus 15 and 57 are congruent modulo 18, but not congruent modulo 10. Similar to the 12-hour clock, which works in modulus 12, the 24-hour clock works in modulus 24, days of the week work modulo 7, and months of the year work modulo 12. There are plenty of uses for modular arithmetic in mathematics and related fields, including the famous RSA encryption algorithm, which protects all of your online passwords. Now, modular arithmetic is a theoretical concept, which doesn't allow for a lot of hands-on use or experience, unlike the second topic in today's video, which is quite the opposite. Getting back to your long-awaited Disney trip, 1 p.m. rolls around and you run downstairs, find your mom, and wrap yourself around her leg, beaming a smile as wide as the kitchen up at her. She looks down at you and says, "Okay, it's time to go. Get in the car." You rush into the garage, climb in the back seat, and strap on your seatbelt, kicking the passenger seat in front of you with excitement. Your parents bring your sister, dressed in her fairy princess outfit, sit her down next to you in the back seat, and the car takes off. About 10 minutes into the drive, you look out the window and your dad is getting on the highway. All of a sudden, you feel an immense pressure on your chest, and it feels like you're being pushed backwards into the seat. The feeling only lasts a couple of seconds, and then everything returns to normal. That was weird. For the rest of the drive, you listen to your favorite Disney songs on repeat with your headphones, making sure to ask for updates on arrival time at regular intervals. Approximately 1.7 eternities later, you exit the highway and approach a stoplight. Suddenly, you're jolted forward, but your seatbelt catches you and holds you back. Ouch! After a few seconds, you're thrown backward to your original position with an uncomfortable scrape on your neck. What's going on? This was one of your earliest experiences of acceleration. Acceleration is a measure of how fast something is increasing in speed with respect to time. When your father entered the highway, he stepped on the gas, and this caused the car to increase in speed. At first, the increase was small. But as the engine revved, the increase became larger and larger every second, which increased the acceleration, and from Newton's second law of motion, this gave you a sensation of a heavier and heavier force pushing you backward into your seat. Then, when you pulled up to the stoplight, your father stepped on the brake, and this produced a force in the opposite direction, pushing you forward until your seatbelt caught you. Other examples of this you may have experienced were takeoff and landing while flying on airplanes, braking while riding your bike, or running face first into a door. It wasn't until you reached your high school physics class or first calculus course that you learned the mathematics behind acceleration. The instantaneous change of velocity is associated with a derivative, and gravity is a special example of acceleration. Those were 2 examples of mathematical concepts that you learned as a child. Can you think of any others? Make sure to tune in again next week as we take a little bite out of another fascinating topic.